I'm from UC San Diego, and I'll be talking today about our work EdgeRIC, a platform for delivering real-time intelligence to cellular networks. This is a joint work between UC San Diego and the Texas A&M University. Towards cloud-native everything. Most of the next-generation applications, such as Internet of Things, extended reality, and autonomous vehicles need cloud assistance. As devices get smaller with limited form factor and limited compute on board, the dependence on the edge to offload much of their computational tasks is fast rising. And the key enabling technology for all these diverse mobile devices to reach the cloud are going to be cellular networks. At the same time, all these applications have diverse network requirements, varying desires on throughput, latency, or reliability. This necessitates tailored network function decisions, and the one-size-fits-all cellular network approach is fading, raising the need to be replaced by an adaptive application-specific model. To do so, the cellular network's functions must be infused with intelligent decision-making capabilities to support this highly dynamic application traffic of these mobile end users over the wireless medium, which is known to be a notoriously unpredictable environment. And there is a need for a decoupled framework to exist that can basically feed the network with these intelligent decisions, what kind of actions to take given the current state of the system. And decoupling is extremely essential because we do not want to break the tight timing guarantees of the radio access network. And such a framework is popularly known as the RAN Intelligent Controller, or RICs. And in support of this notion, the industry is moving towards the idea of open radio access networks, moving away from the traditional monolithic cellular stack or a black box proprietary infrastructure to one with open interfaces, disaggregated network components, and softwarization to facilitate flexible updates and interoperability. To get a quick primer on the current network infrastructure, we have these radio units at the physical cell edge, which is mostly responsible for the transmission and reception of the radio signals. This unit connects to the distributed unit, which handles most of the signal processing functions, such as MCS selections, beam management, resource scheduling, and so on. And all of this together basically constitutes the physical network edge. The DUs then connect to the central units, which is hosted in the cloud in a data center located some distance away from the network edge. And the CU is mostly responsible for higher layer RAN functions pertaining to packet processing. The CUs basically connect to the core network, which acts as the gateway to the rest of the internet. The application servers or the edge servers are also located in the cloud. So it is the cloud which is very information rich in terms of both the application and the network states. The ORAN also talks about situating the RAN intelligent controllers or the RICs in the cloud to corroborate the RAN with the desired intelligence. The timescale of operation of each of these units is as follows, and we see here that the physical network edge basically operates at the granularity of the transmission time interval, or the TTI, which is 1 millisecond at most. But the cloud-hosted RICs are designed to deliver intelligence at a time scale between a few hundred milliseconds to a few seconds. And these are only great for macro-level network reconfigurations, the use cases being network slicing, traffic steering, load balancing, and so on. So what is the issue with the existing design? The cloud RICs can impart control decisions at the granularity of, at best, 10 milliseconds to 20 milliseconds. But the underlying wireless channel is fast changing, and the channel stability time, in fact, goes down as the mobility of all these devices increases. So the question is, can these existing RICs react fast enough to mirror the underlying channel variations? And as seen from real-world measurements, the channel indeed changes quickly. We have a variety of UE devices under various mobility scenarios, and this is a CDF of how fast the channel quality indicator, or the CQI, is changing. And we see that for almost 60% of the time, channel changes in less than 5 milliseconds. Moving on to the next issue. We have seen before that the application states are only available in the cloud. So the lower layer stack, that is the DU functionalities, is agnostic to what applications are running underneath. And consider this system scenario where we have both the users which are running in a very high data rate network slice, but one user is basically running a file downloading application, and we have the other user running an augmented reality application. So a traditional in-stack resource scheduler will treat both these users equally in the slice and allocate equal resources to both of them, which can lead to choppy videos, and this might degrade the quality of experience of the AR user. Thus, it is very important that the functional decisions, even at the last stage of the data delivery pipeline, be application aware to truly deliver a QoE optimal network. To that end, we introduce EdgeRIC. Our design is basically driven by the objective of infusing application-aware real-time intelligence into network functions and decisions at the network's edge. And this approach is particularly crucial for making informed decisions based on my current instantaneous channel conditions. And by situating this decision-making process closer to the RAN edge, we ensure that the channel metrics utilized are as current and relevant as possible, as opposed to being relayed from a distant cloud infrastructure. Thus, EdgeRIC can enable unprecedented lower layer intelligent optimizations, but with a disaggregated compute model running as a microservice. These microservices operating at the microsecond timescale is what we refer to as microapps. And we adopt a disaggregated approach here because in case a control decision cannot be imparted within the TTI interval, the RAN can fall back to its default policy. Our key contributions for this work is as follows. EdgeRIC is designed to be operating in real time, maintaining a 1 millisecond synchronization with the radio access network. EdgeRIC is facilitated to leverage immediate edge-based data while still drawing on the broader perspective provided by cloud level analytics. It does so by sharing a common database with the cloud-based systems. EdgeRIC is built on top of open source cellular stacks, and our platform is available for community research. Our platform supports easy micro app development with off-the-shelf ML code bases. Specifically, our work is built on top of the SRS RAN code base. Finally, we also provide an emulator module to support the offline training of AI ML policies. Putting all of this together in the last section of my talk, I'll be showing an example micro app in action over EdgeRIC, thus demonstrating real-time AI in the loop with over-the-air experimental results. Showing the key results as observed as a result of real-time control. We have scheduling decisions which are made at the TTI timescale. It supports a much higher system throughput as opposed to delayed decisions when implemented with cloud-based RICs. EdgeRIC can support a throughput increase by almost 25%. An application-aware scheduling decision imparted in real time significantly reduced the video rebuffering time or the stall duration for a video streaming use case. Reduced stall duration yields better user experience, and that is what we observe with EdgeRIC. Coming to training of AI policies, model converges optimally with real-time data, whereas with delayed samples, the training is quite flaky and it in fact converges only suboptimally, as these delayed samples may tend to break the correlation between the state and action. Now, I'll be going over how each of these features are implemented. Most importantly, we need a lightweight messaging framework, so we develop our own real-time variant of the E2 interface, which is the standardized interface for RAN and RIC communication. We call it the RTE2, built on top of the 0MQ message passing framework, owing to its lightweight nature, low latency, minimal overhead, and compatibility with various IPC TCP modes. Next, we have the RAN to EdgeRIC message, which we call the RTE2 report. This is a periodic pub-sub procedure under which the RAN publishes some information every TTI. Micro apps at EdgeRIC may subscribe to this RTE2 report and utilize it for inference and control. The EdgeRIC to RAN message is then called the RTE2 policy. This is also an event-driven pub-sub procedure under which the micro app at EdgeRIC publishes information to the DU, which is picked up for real-time control. Next, what we need is basically a TTI level or a 1 millisecond synchronization with the radio access network. Our system is synchronized to the TTI level clock tick from the RAN stack. And the RAN uses a counter every TTI, which we refer to as the RAN index. And this RAN index is included in all the messages from RAN to EdgeRIC in the RTE2 report. EdgeRIC2 maintains its own counter called the RIC index, and it increments by 1 every time it sends out its action. And our system is equipped with a default mechanism to ensure that EdgeRIC is always slaved to the current RAN index or the TTI by ensuring that our RIC index is always equal to the RAN index. For micro app development, we have the EdgeRIC, which features interfaces for real-time communication, and these interfaces connect to an OpenAI GIM wrapper, which abstracts the collected metrics into a GIM-compatible environment. OpenAI GIM is a Python-based open source library that provides a framework for developing an interface to interact and query the environment by any given algorithm, thus making it a very popular reinforcement learning framework. And this design enables any micro app developers to employ custom AI/ML-based strategies for the lower layer RAN functions. Thus, micro apps can be easily integrated with this standardized framework and facilitating efficient development and deployment within our EdgeRIC ecosystem. Our architectural framework does not strictly confine EdgeRIC to only edge-centric metrics. EdgeRIC is designed to share a common database with the cloud-based systems because our design philosophy is based on a cloud and edge collaboration to harness the full potential of next-generation cellular networks. To do so, we have EdgeRIC incorporating an in-memory Redis database for managing all the real-time metrics it receives from the RAN and also to receive data from the cloud for the higher level network analytics. And this is also used to store the trained AI policies coming from the cloud for deployment over its various micro apps. Finally, our EdgeRIC emulator module. This module leverages actual RAN and software UE code bases, but uses virtual radios to emulate the channel. The complex valued baseband IQ samples coming from the radio access network are routed through 0MQ source and sink sockets. We have a GNU radio flow graph which then distributes these IQ samples to the various users, and users can be launched under various network namespaces, and applications can be run end to end. And the channel effects can be introduced for each UE through signal processing blocks over GNU radio or with using real-world channel traces. And in the same module, we can connect EdgeRIC, thus giving us a full system all in one physical machine. And this is great for network data generation and offline policy training. Now we shall demonstrate the example micro app running on EdgeRIC, which targets the resource scheduling function at the MAC layer. We will be leveraging a reinforcement learning strategy to deploy our policy model. We demonstrate improvements on the following two scenarios. In the first scenario, we focus on a very simple environment to assess the benefits of real-time intelligent decisions. Here, our policy is basically trained to maximize the total system throughput. In the next scenario, we consider a system with users running a real-world video streaming application. Our agent focuses on improving the quality of experience of the users by incorporating application state awareness. Our training is performed completely on the emulator module. The environment for the RL agent consists of the RAN stack and the application information from the cloud. For every action taken, a state and reward is generated, which aids the policy training. The trained policy is transferred to EdgeRIC to run as a microservice, and during system execution, EdgeRIC receives the states, uses a trained model to decide an action which is sent back to the RAN. And in this case, the action is basically how many resources to allocate to each UE. So our scenario 1, consider the system scenario where we have two users running very high data rate traffic. The state space for our RL agent here is the channel quality and the backlog queue of each UE as seen at the network. The agent is trained with the objective of maximizing the total bytes transmitted for every action taken. We use an off-the-shelf RL policy, the proximal policy optimization in this work. This is a simple scenario. The training converges quite fast in roughly 40 iterations. In execution mode, we have the micro app which receives the states from the RAN and sends out the scheduling action. So here our micro app policy enhances the total system throughput with real-time decisions. Here is our experimental setup with two users and the radio access network which is equipped with EdgeRIC. what we see on screen is the real-time throughput. First, we deploy this traditional instack scheduler, precisely the max wait scheduler that runs on EdgeRIC as a micro app, and we switch to the RL policy. As models get trained, we see that the throughput slowly increases, and the throughput gets better as the model is fully trained. A fully trained model can definitely support a higher system load as compared to traditional algorithms when run as a microservice over EdgeRIC. Here, thus, we demonstrate real-time AI in the loop for decision and control. Then moving on to scenario 2, consider the scenario where we have two users running a video streaming application. The state space for our RL agent here is basically the channel and the backlog of each user as seen at the radio access network, and the state is further augmented with the application state, that is the playback media buffer at each client. The agent is trained with the objective of reducing the rebuffering events which occurs as a result of the media buffer falling below a certain threshold, and a high negative reward is given in case of such an event. The micro app receives the states from the network and sends out the scheduling action. So we have the micro app policy that reduces the video rebuffering time with application state awareness. What do we get out of this? Our RL policy significantly reduced the stall duration, thus enhancing the quality of experience of the end users. Basically, traditional schedulers fail in cases when the media buffers are low and at the same time the channel is bad. They tend to prioritize users with better channel conditions in order to maintain a good overall system throughput. Here we see, so basically we are running a dash-based video streaming application with 2-second video chunks, and all chunks are requested at the same fixed bitrate. While traditional algorithms like MaxBait are application agnostic, we can see that the media buffer falls below the minimum threshold, which gives rise to these long rebuffering events, whereas our application-aware scheduler is able to recover quickly from these rebuffering events, delivering a better quality of experience. With that, I can conclude my talk, and I would be happy to take questions.